Welcome to session 5 of Unit 4 of our financial modeling course. In this session, we are going to consider model specification, that is, as to how to specify our model or how to select the best model for our estimation. By the end of this session, you should be able to understand and explain the concept of model specification. So, we will ask ourselves, what is model specification? In simple terms, model specification is about choosing the best regression model. According to Jim Frost, model specification is the process of determining which dependent variable to include in a regression model and which not to, or which variables not to include. Remember, model specification is a difficult task given the complicated and the tiring nature of the world. So it is important to note that model selection is a crucial process. Thus, if you don't select the correct model, you have made a specification error, which can invalidate your result. So by specification error, we are simply saying when the independent variables and their functional form inaccurately portray the real relationship present in the data. So specification error can cause bias, which can exaggerate, understate, or entirely hide the presence of underlying relationships, simply meaning you cannot trust the result when there are specification errors. So you need to choose carefully. So how then do we choose in model specification? How do you perfectly choose? Remember that too few models or too few model specification on the specified models tend to be biased. Too many, or what we call the over-specified models, tend to be less precise, and just right model is what we are looking for. So the right models with the correct terms are not biased, and also they are most precise. So to avoid this bias result, your regression equation should contain any independent variables that you are specifically testing for, and also add any other variables that empirically state that, or that empirically depicts a relationship between the variables that you are testing and the regressant. So empirically, the modeling of macroeconomic variables are often done in the log linear form. So mostly, hardly do we consider linear form or linear models in testing for most macroeconomic variables. A very good example is to test whether the linear form of the Cobb-Douglas production function will perform better compared to the log linear form of the same. Remember, we earlier said that there is a chance that, or not all regression models are linear. We have the polynomials, we have the spline form, and other forms of regression. And also, we made it clear that the log linear or the double log form of regression analysis mostly works better because most data exhibits that form of non-stationarity, and therefore you have to difference it with the use of log transformation or the logarithmic transformation. So in applied work in economics, it is often the case that statistical work is done using the logarithms of variables rather than the raw variables themselves, as we said earlier. So time series variables that grow at a constant percentage rate will have their log as a linear function of time. So we are saying that when the price series are constantly increasing over time, if we find the log of this price series, it will simply be the linear form of that particular series, or that particular series. So again, many theoretical relationships in economics are non-linear according to Mishina 2003, but in this case they are saying that they are linear when we find the logs of those variables. So for instance, according to Lukpo and Zhu 2012, in time series analysis, the log transformation of variables is often considered to stabilize the variance of a series. So we're talking about the issue of stationarity. We're saying that when we find the logs of these variables or this time series data, there's a chance that we're going to find a stabilized data set compared to the raw data set. So in this further example, we would like to transform our variables, that is from the macroeconomic variables that we used earlier, that is the adjusted inflation, the petroleum price, among others. We like to find their logarithmic values and then compare these values, the regression analysis or the regression results from these logarithmic values to the original values. So the table 3.29 is simply a log regression of the original model, that is the first regression time series analysis that we did. So you could clearly see that except for the intercept, there is a stark improvement in coefficient of determination and the significance. So except these coefficients, these ones, there is an improvement in the coefficient of determination, that is the R squared, and the significance of the coefficient in the double log model from the linear model. So there have been an improvement from the probability value, even though it is still not significant, but we can find that the loss of the treasury bills is now significant compared to the previous one, as the from the first example, that of the treasury bill was still insignificant. Here we can definitely see that of even the petroleum price is now significant compared to the previous statistics, indicating that the log transformation is. So this simply indicates that the log transformation of the datasets makes it significant, or makes testing quite significant. So we can definitely observe that there have been some form of significance compared to the previous one, that were most of the variables were insignificant, with the exception of the lag values of the dependent variable itself. So we can now conclude that the model with the log transformation, or the log transform model, is quite perfect, or is in a way performs better compared to the raw values. But comparing the two, we cannot just use these values to compare the two. We have to go beyond this simple regression analysis in comparing both the linear form or the raw form of the variables and the log form of the variables. So we will consider this in the next session. So to be able to compare two models, that is in our case the original model and the log form of the original model, we have to start by computing the geometric mean of the theta deposit, that is the dependent variable or the regressant, and then we construct a new variable weighted with the geometric mean of the theta deposit above, and then we estimate the model just as we did in our previous table, with the new variable as regressant. Then we re-estimate the log of the new variables as a regressant instead of the log theta deposit. We will then obtain a residual sum of square for the first and second observation, of the first and second process that we conducted from these two new models, and then we also get a chi-square distribution. So if the chi-square value compute from the 3.6 is statistically significant, we can then conclude that the model with the lower residual sum of square is a better model. So we cannot just compare the regression model or regression analysis from the two different model, but we have to go beyond it, and this is one of the ways that we can compare two models to see whether one is better than the other. So in this session, we have discussed the relevance of log transformation in modeling, and we have further explained the concept of model specification. Thank you.